Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog. Today we'll be talking of another form of energy which is equally important for all of us. And when I say talking, that's exactly what I'm going to do of. We'll talk of sound energy. Realize that it is one of the most important ways in which humans have been communicating with each other. And so it's very important that we have some basic idea of what sound is, how it is produced, what are the basic scientific ideas related to sound, how do we humans use sound, and then another interesting area, which is how music is produced and how we have different forms of sound that make life very interesting. So let's begin. Sound is a form of energy, as I told you long back. And it is produced because of what are known as longitudinal waves. These are mechanical waves, um, and they cause a change in pressure and density as they move forward through any elastic medium. So, when I am talking, I am creating certain vibrations, which is because of oscillations of some of my body parts, which I am going to discuss later on sometime. And these vibrations cause vibrations in air, resulting into some particles coming closer and some moving away, resulting into energy being transferred from one point, which is my throat, right up to the microphone through which the sound is reaching you people. So these are mechanical waves and they need an elastic medium. Some of the most important things that we must know about sound are two things. First, vibrations and what is the way or the number in of times vibrations take place or oscillations take place, and these are typically known as frequency of the sound waves. The unit that is used to measure it in the olden days was cycles per second, but that's all outdated now, and we measure it in terms of what is known as hertz. So 1 hertz means one vibration in 1 second. So it could be 10 hertz or 100 hertz or 1000 hertz. The instant you go to 1000, you don't talk of 1000, but you say kilohertz. And if it keeps on increasing and goes to 1 million, then we say megahertz. And if it becomes 1000 megahertz, then it is treated as gigahertz and so forth. We talked of some of these numbers in our previous lecture. So that's one area, frequency. And the waves are produced in a medium. And what happens is the whole thing repeats itself after a certain amount of time. The time interval in which a wave completes one vibration is typically referred to as its time period. And in that time, whatever is the distance covered by the wave is typically referred to as its wavelength. And this wavelength is measured in terms of meters, or if it is very small, in terms of centimeters. And if it is extremely small, as in case of light, which we will come to sometime later, it's measured in terms of nanometers or angstrom units. But that's a later part. Let's keep that aside just now. And so I have frequency and I have wavelength. And if I multiply the two of them together, what I get is an equally important term in sound, which is the speed at which sound travels. So, speed is how much a wave travels in 1 second, that is wavelength, multiplied by the number of oscillations that take place, which is nothing but the frequency. So I multiply the frequency by the wavelength and it tells me how much distance the disturbance because of a wave travels in a particular direction. If it travels only in one particular direction, which doesn't really happen in case of sound, it is referred to as its velocity. But let's keep that aside. And how much is this velocity? We know the numbers. Um, it travels 331 meters in 1 second. That's at 0 degrees Celsius, but none of us live at 0 degrees Celsius. So, normally at the temperature that we are, that is around 28, 29 degrees Celsius, the velocity is, or the speed of sound is around 340 meters per second. Now, when I'm talking, I'm producing certain frequencies. So, what are the frequencies that humans normally hear? These are typically referred to as threshold frequencies. A normal human being can hear frequencies that are anywhere between 20 hertz, that is 20 vibrations in 1 second, up to 20,000 hertz, that is 20 kilohertz. And if I convert it in terms of the wavelength, for 20 hertz, the wavelength is 17 meters. And for 20 kilohertz, the wavelength is 1.7 centimeters. So, if I talk in terms of wavelengths, then I can hear sound that has a wavelength of anywhere between 17 meters and 1.7 centimeters. Let me also remind you that lower the frequency, higher the wavelength, and lower is the net amount of energy possessed by that particular wave. And the higher the frequency, the value of the wavelength starts going down. I must point out one more thing. What I have referred to is threshold values for human beings. For other animals, the values are different and they are equally important sometime. I'll come to that a little later. Now, what does this speed depend upon? It depends upon two factors. One, as I told you, first of all, it needs an elastic medium, and it is the density of the medium that matters. More the density, less would be the speed at which the wave travels. And more elastic the medium, the faster the wave will travel. But when we start moving from air to other media, the rate at which the elasticity changes is much, much higher than the rate at which the density changes. So, in most cases, we feel that even if the density has become more, the velocity should have become less or the speed should have become less, but it seems to get higher. Just to give you an example, in case of water, the velocity or the speed of sound is 4 times the speed of sound in air. And if I talk of iron, then the speed of sound in iron is 15 times, approximately 15 times the speed of sound in air. So you'll find that through metals and liquids like water, etc., the velocity of sound starts becoming more and more. And if the medium starts becoming less and less, like if there is a vacuum, then the velocity would become zero. So sound cannot travel without a medium. So we see the sun because the light comes in the form of electromagnetic waves. But we can't hear the sound that is produced in the sun because in between the sun and earth there is a vacuum. So it's not possible to hear the sound that is being produced within the sun. Now, what else do we need to know about sound? Commonly, we hear four typical words: um, subsonic, supersonic, infrasonic, and ultrasonic. They're equally important words because we hear of them quite often. Let me clarify what they are. Many a times there is a confusion. They all are just two different ones. That's all. That's not true. Subsonic and supersonic deal with the speed of sound. If an object has a speed less than the speed of sound, it is said to travel at a subsonic speed. And if an object travels at a speed greater than the speed of sound, it is said to travel at a supersonic speed. Let me also remind you that we hear of Sukhoi, for example, or F-16 or other planes. These are said to be supersonic planes. Concorde was a flight plane that was designed to be supersonic. That means its speed was more than the speed of sound in air. And how much is that? When I say 340 meters per second, that's not a number that we are really very conversant with. So if I convert it in terms of kilometers per hour, 340 meters per second works out to be roughly around 1225 kilometers per hour. So close to 1200 kilometers per hour is the speed at which if a plane travels, then it is at the speed of the velocity or the speed of sound. Anything more than that means the plane is a supersonic plane. And there is a number that is used to identify this. It was first mentioned by an Austrian scientist called Ernst Mach. And so this is typically referred to as Mach number. So if Mach number of a plane is 2, it means that the ratio of the speed of the plane to that of sound is 2. That means it travels at twice the speed of sound. And if it is Mach 3, it travels at 3 times the speed of sound. People use this number more on scientific basis, but there are people who also make ads talking of razor blades that go at Mach 3 and cycles that go at Mach 3 and so forth. Doesn't really make any sense because the ads are there to cause more confusion than understanding of what the number really is. And this Mach number values keep on going higher and higher. And it is referred to as supersonic as long as the value is up to about 5, Mach 5. What happens if you go beyond that? Then it is said to be hypersonic. You must have heard of some special missiles that are now being designed that are said to be hypersonic missiles. Their speed is between 5 to 10 times the speed of sound, or their speed is 5 Mach to about 10 Mach, and that is the way it is measured. I must also remind you one more thing. If you are at ground level or close to earth, the velocity of sound is different than the velocity of sound at higher levels. So that has to be taken into account whenever we talk of these Mach numbers for aeroplanes and other objects. So that's subsonic and supersonic. And I talked of two more words. One was infrasonic and the second was ultrasonic. Infrasonic is when the frequency of the sound that is being produced is lower than the frequency that is audible to us. That means the frequency is less than 20 hertz. And if the frequency is more than 20,000 hertz or 20 kilohertz, we humans can't hear it because it is beyond our threshold. And such sounds are said to be ultrasonic sounds. So ultrasonic is associated with frequency. Infrasonic is associated with frequency. Infra is lower, ultra is higher. And why is it important? Two reasons. Ultrasonics, we all know. Whenever we talk of sonography and other medical processes, the sound waves that are used to penetrate our body and get pictures are ultrasonic sound frequencies. How they are used is something that I will talk of maybe much later when I start talking of medical equipments. And what about infrasonic? Infrasonic is when very large objects begin to vibrate, but then they vibrate at a very low frequency. This is a frequency that I am producing. But if the tectonic plate of the earth starts vibrating, The vibrations and the energy could be very high, but the frequency will be very low. There are some animals that can hear this frequency, and dogs and horses and birds are all capable of listening to this infrasonic sound. And so it is known fact that when earthquakes are about to happen, the ground, as soon as it begins to produce these frequencies, it is dogs and horses and animals which can hear this very large sound start reacting to it immediately. So birds and dogs and animals trigger the process of realization of an imminent earthquake many a times. And birds are capable of listening to higher frequencies also. And we are aware of echolocation, something that was taught to us in school. And we were told that bats can travel at night without colliding with things because they generate an extremely high frequency and can listen to this high frequency note which we cannot. And so that frequency is invariably ultrasonic frequency. So these are the four typical words. More details of this I will talk when I come to some applications of sound, maybe sometime later. Subsonic, supersonic, infrasonic, and ultrasonic. And all of them have their own uses. But what happens to a wave when I talk? It reaches your ear and it gets detected and you start responding to the sound. But suppose the wave goes and collides with a wall, then a part of the wave turns back. And that is a reflection of sound. And that results into what we all know of echo. For echo to be heard, the reflected sound must reach back our ear at least one tenth of a second later than the original sound. In one tenth of a second, sound would travel 34 meters, which means 17 meters till it goes and collides and 17 meters back again. So only when a reflecting surface or a wall is at least 17 meters from you would you be able to hear an echo. So when you stand on top of a mountain and start screaming and the opposite mountain is more than 17 meters far away, which obviously it is, the sound would travel up to there, turn back, and you would start hearing the echo. Naturally, in the process of traveling and coming back, a lot of energy is lost. So the sound level drops and the echo is always much weaker. But then there is another possibility. You stand within a very big dome, like what is there known as the Gol Gumbaz, and you produce a sound note. And so it starts reflecting at different points along the walls of the dome. And the distances are more than 17 meters. Each reflection turning back to you produces one sound, and so you start hearing multiple echoes. So that's how multiple echoes are produced. Just listening to echoes, that's not important. There are many other applications too. Just to remind you of what they are, we'll talk of their details sometime later. There is a word called sonar, sound navigation and ranging. That's the one that is used by submarines. They use a sonar sound which sends a pulse out, collides with the object in front or below, and turns back. And then that sound is recorded, and you can judge the distance. And many other things too, like what we talked of when we talked of petrol. Detection of petrol and various parts underground or many minerals underground can be done by using these uh, techniques of sending sound waves deep down and getting them reflected. Instead of sound, if you start using light waves or radio waves, what you get is typically known as radar, radio detection and ranging. But that's a different issue. Let's talk of that sometime later when we come to light. There's one more thing that we notice about sound. If you close your eyes and listen to a vehicle that is coming towards you, you will feel that it produces high pitch frequency. And the instant it crosses you, it starts producing bass notes. If you're standing on the railway platform and a train passes by, you notice the same thing. The whistle appears to be extremely sharp as the train approaches, and it suddenly broadens out as soon as it crosses you. And a plane that flies overhead or a motorcycle that passes by, the same thing happens. This effect is known as Doppler effect, and it's a very important phenomenon because it is used at a variety of scientific levels. Doppler effect is used in medicine. You must have heard of the words like color Doppler effect and so forth. And it is used to prove one of the most important factors, but not in sound. It was used in light. And the concept of the Big Bang, how the universe started, is proved because of Doppler effect of light. I'll come to that sometime later. Please realize that depending upon how fast or how slow the source or the listener moves decides on this effect, which is known as Doppler effect. So Doppler effect then is an equally important effect that we always hear but are not aware of what happens. Common sense will tell you a very simple thing. If an object is stationary and another object is moving towards it, the waves there will tend to get compressed because of the motion. And so the frequencies will appear to be a little higher. And so the sound would appear to be of higher pitch. And the instant it crosses over, the wavelengths would become bigger. So naturally, the frequencies that you seem to hear would become of lower values. And that is the low pitch sound that you hear than the original. That's the basic idea of how Doppler effect works. There are many more applications, but those I'm sure we can talk of much later. What else do we know about sound as science? Let me remind you of one more effect, and that is equally important. Suppose I send a wave, it collides and turns back. So the two waves are going to cause an effect on each other. Remember what we talked of when I talked of the radio and how one wave gets superimposed on the other? Same thing is going to happen here. A wave comes from one side, an identical reflected wave comes from the other side. They superimpose on each other. So, do they cancel out each other? That doesn't happen. It produces a new pattern of wave, and that is known as a stationary wave. And it is this stationary wave that is the source of many of the sounds that we produce. It results into certain points that have no vibrations left at all. These are typically referred to as nodes. And there are some points that begin to vibrate a lot more. And these are known as antinodes. And these nodes and antinodes produced anywhere around us is the way in which sound is produced, not only in music, but in musical instruments and even through our throat muscles. How that works out is a discussion I'll come to sometime later. These are some of the basic ideas that we need to know about sound. But how do I produce sound? And how do I respond to it? How do I hear sound? That's something that we will discuss next time. If you have liked whatever I have said, please tell your friends about it. Read a little bit more if possible. Appreciate the many concepts in sound that we are going to discuss soon. Like and subscribe to this channel. Until we return on science once more, to understand how sound is produced and how we hear it as the second step in sound. Till we meet again, Namaskar.